Welcome back. Today, we're looking at a piece of technology that essentially runs a high-stakes microscopic race, HPLC, or High Performance Liquid Chromatography. In this explainer, we're going to break down exactly how this machine separates the invisible building blocks of the world around us.
Okay, let's dive into this. Here's our roadmap for today. 1. The separation challenge. 2. Anatomy of the HPLC. 3. The microscopic race. 4. Modes of separation. And 5. Reading the results.
Section 1. The Separation Challenge, Finding the Invisible. Now, you might be wondering, if you have a complex liquid, say a water sample from a local river, or maybe a newly synthesized pharmaceutical drug, how do you actually separate and identify an entirely invisible mixture? How do you trace a microscopic toxin? Or prove without a doubt that a life-saving medication is pure? Well, that is the massive, real-world problem that HPLC solves. And it's hard to overstate just why this matters. The industrial applications are absolutely massive. The pharmaceutical industry relies on it heavily to analyze the purity of drug components. Over in environmental testing, it's used to detect trace toxins in soil and water. The food and beverage industry depends on it to ensure strict safety standards. And the sensitivity? It's literally mind-blowing. An HPLC system can detect trace concentrations down to parts per trillion. To put that into perspective, it's the chemical equivalent of finding one single specific grain of sand on an entire beach.
Section 2. Anatomy of the HPLC. Power and precision.
400. That's the amount of pressure, in bars, that a standard HPLC system operates under. That's roughly equivalent to 40 megapascals. Because we're forcing a liquid mixture through some incredibly dense materials, a high-pressure pump is absolutely essential to generate this immense driving force. We have to build a powerful racetrack before we can actually race. So the crucial point here is how the sample actually travels through the machine. Let's trace that physical path. First, you have the solvent reservoir, which holds the liquid that'll push everything along. Next up is that massive high-pressure pump we just talked about. Then, the injector, or autosampler, introduces our complex mixture right into that pressurized flow. From there, it enters the column, which is really the heart of the whole system, before the separated components finally hit the detector at the very end. Let's focus on that column for a second, because this is where the actual separation takes place. It's a stainless steel tube, usually just 5 to 25 centimeters long, and it is tightly packed with chemically modified microscopic particles. It relies on that heavy-duty stainless steel casing to safely contain that intense 400 bar pressure. So this densely packed, surprisingly small tube forms the actual track for our invisible race. Section 3. The microscopic race. Differential partitioning. To really understand how this race works, we need to meet the two main players setting up the environment. First is the mobile phase. This is the moving liquid solvent that gets pumped through the system. Think of it as a continuous flowing current pushing our sample molecules forward. Interestingly, scientists often use a technique called helium sparging, where they bubble helium gas through the solvent beforehand. This degasses the liquid, which is super important to prevent unstable baselines when we eventually read our final results. The second player is the stationary phase. This is the fixed packing material inside that stainless steel column, often some form of chemically modified silica. You can think of this phase as a highly complex obstacle course. Because these particles are uniform and incredibly small, usually just 3 to 5 micrometers, they create a truly massive internal surface area for the sample molecules to interact with as they get pushed through. And this brilliantly illustrates the core mechanism of the whole machine, differential partitioning. If a molecule in our mixture has a high affinity for the mobile phase, it's kind of like a surfer catching a fast wave. It just ignores the obstacles and shoots out of the column early. But if a molecule has a high affinity for the stationary phase, it stops to interact with all those microscopic obstacles. It gets significantly delayed. So the mixture separates simply because the different molecules end up traveling at completely different speeds. Section 4. Modes of separation. Customizing the racetrack. The cool thing is, scientists can completely rewrite the rules of the race depending on what molecules they're trying to separate, just by playing with polarity. In normal phase HPLC, the stationary phase is polar, like pure silica, and the mobile phase is nonpolar. This setup traps and retains polar molecules, letting the nonpolar ones win the race. But in reverse phase HPLC, they totally flip the script. They use a nonpolar stationary phase, like silica modified with C18 or C8 carbon chains, alongside a polar mobile phase. Now it's the hydrophobic nonpolar molecules that get delayed, and the polar ones speed right through to the finish line. And, we aren't just limited to polarity. Take size exclusion chromatography, for example. This uses porous particles. The small molecules wander into these tiny pores and basically get lost in a maze, while the large molecules simply bypass them and wash straight down the column. It completely flips our intuition, right? It lets the biggest, bulkiest molecules finish first. Alternatively, there's ion exchange, which separates the mixture based strictly on the positive or negative electrical charge of the molecules.
We can even change the track conditions while the race is actively happening. In isochromatic elution, the liquid mobile phase composition remains exactly the same from start to finish, steady and consistent. But in gradient elution, the machine automatically alters the chemical mixture of the mobile phase mid-race. This is a huge deal because it lets scientists fine-tune the purification process, coaxing highly stubborn molecules out of the column by slowly changing the chemical environment around them. Section 5. Reading the results, crossing the finish line. Okay, so what happens when they finally finish the race? Here is how we capture the data. First, the molecules elute, meaning they exit the column and flow directly into a detector. A very common setup is the UV-vis detector, which shines ultraviolet and visible light, often using deuterium and tungsten lamps right through the flow to measure exactly how much light our newly separated molecules are absorbing. Now, UV-vis is just one option, alongside things like infrared, fluorescence, or mass spectrometers. But finally, whatever detector is used sends this data to a computer to generate a visual graph, which we call a chromatogram. Now, what's really interesting about this is how we actually identify what we're looking at. To ground this concept with a concrete example, we use known standards. If we run pure glucose through our system and it takes exactly 5 minutes to elute, 5 minutes becomes its known retention time. If pure sucrose takes 8 minutes, well, that's its retention time. Later on, when we're testing an unknown mixture, if the detector spikes at exactly 5 minutes, we can confidently say, yep, that's glucose. So when you're reading the final chromatogram, the x-axis is showing you that retention time. That answers the qualitative question, what is the identity of this substance? But the y-axis, or actually more accurately, the total area under that peak, represents the concentration. That answers the quantitative question, how much of this substance is actually in the sample. A massive peak area means a high concentration of that specific molecule was present in our original mixture. Which brings us to the cutting edge. Standard HPLC is amazing, for sure, but ultra-high-performance liquid chromatography, UHPLC, is pushing the boundaries of extreme engineering. With next-generation systems being developed to handle up to 6,800 bars of pressure using incredibly tiny 1-micron particles, we really have to ask how much faster and how much more precise will the molecular races of tomorrow be? The ability to analyze the invisible world is only getting sharper. Thank you so much for joining me on this explainer, and I hope this gives you a whole new appreciation for the microscopic obstacle courses operating in labs all around the world.